Okay, so from time to time, it's going to be useful to us to be able to identify the frontier orbitals that are involved in a particular chemical reaction. And we'll get into the reasons of why that might be useful in a couple of minutes. So our starting point for that would be what's called a chemical mechanism. Okay, now, a mechanism, just to remind you from chemical kinetics that you saw in Gen Chem, is a step-by-step description of how a chemical reaction is occurring. So a step-by-step description of how a chemical reaction occurs. Now, in general chemistry, when you wrote mechanisms, you wrote a series of equations. So step one, there would be a chemical equation. Step two, a different chemical equation, and so on. We do pretty much the same thing in organic chemistry, except that we're drawing the mechanisms using the curved arrow notation that we use for resonance. And just like there, the arrows are always going to originate at an electron, whether it's a single electron or a pair of electrons, and it's going to point to where those electrons end up in the next picture that we draw. So in this example, the electrons are originating here. It's the lone pair of electrons that A is using to form a bond to B. And the curved arrow notation that you would use shows how you would do that. So like so, you would point to just next to B. So start the arrow at the lone pair on A and point at B or right next to it. Now those same electrons are now present as a pair of bonding electrons in an AB bond that we just made. Now in this example, A is the one that was supplying the electrons, and in this context, it's a nucleophile. So a nucleophile is something that provides electrons to the other reactant. And so if you're going to provide electrons to somebody else, you have to have available electrons to do that. Oftentimes, but not always, the nucleophile will have partial negative charge or full negative charge somewhere. B in this example is playing the role of the electrophile. So nucleophiles react with electrophiles. Electrophiles accept electrons from the nucleophile. To do so, the electrophile has to have an empty orbital. And often, but not always, the electrophile will be associated with partial positive charge or positive charge. Okay, so when you're drawing the mechanism, let's redraw this mechanism down here. So we had A with a lone pair reacting with B. So if you know these two are going to bond, just imagine that bond between the two of them. Start the arrow at the pair of electrons, and then the electrons end up in the bond, so point to that imaginary line. But get it kind of close to B so that it's clear what's going on. And then, of course, the result of that is this. Okay, so why do we care about frontier orbitals? Why are frontier orbitals important? Well, for starters, frontier orbitals, understanding some things about frontier orbitals, allow us to answer questions, for example, like, will A react with B? Well, the answer to that would be yes, as long as their frontier orbitals are, let's say, well matched. So we'll say yes with the caveat that if the HOMO of A and the LUMO of B have a good energy match. That means they're close to each other in energy. And efficient overlap. Remember, you can't make a bond unless the overlap between the orbitals, the involved orbitals, is decent. So A will react with B as long as their HOMO and LUMO are well matched in energy and have good overlap. Now, another thing that you learned about when you studied chemical kinetics had to do with the fact that when two chemicals approach each other, they have to do so at the right angle. The trajectory of their approach has to be a certain trajectory. Okay, so two chemicals can't just react by any collision at any angle. So a question that we can also ask here is, what is the best trajectory or approach for A and B to react? The answer to that is that the best approach is the one that gives you the maximum overlap between the involved frontier orbitals. So the best approach is the one that provides maximum overlap between the frontier orbitals. Now, are we going to look at these things every single time we talk about a reaction? No, not necessarily. But a lot of the reactions that we're going to be studying have particular outcomes that can be rationalized or understood if we understand some things about the orbitals involved. So these are two of the main questions that people ask and use frontier orbitals to answer. Okay, so the next thing we're going to do is draw some mechanisms. Now, these are not mechanisms that you need to memorize at this stage of the game. These are mechanisms that involve reactions that you'll see later this semester and next semester. So we're just going to use them so that we can learn how to interpret what's going on in these mechanistic pictures. So at the top of the page, it says, how to identify frontier orbitals in a reaction. Okay, well, we're going to fill that in a little bit later. What we're going to do first is work through the examples, and I'm going to talk you through what you would do. So let's look at this first example. That's the between methyl iodide, and hydroxide ion. So let me draw those two things. So here's a hydroxide ion. And then this is the structure of methyl iodide. Okay, when these two get together, what happens is the following. The hydroxide ion decides that it wants to form a bond to carbon. And so it uses one of the lone pairs on the oxygen atom to bond to the carbon. And if we stopped right here, the carbon would have 5 things bonded to it, which means it would have 10 electrons around it, which we can't have. That's a heinous violation of the octet rule. That means that a pair of electrons has to move away from the carbon, and the way that that happens is that the iodine takes that pair of electrons and takes off. So what you end up with is a new carbon-oxygen bond. The carbon-iodine bond broke, and the iodide ion ended up leaving the molecule. So the iodine took its 3 lone pairs as well as the pair of bonding electrons that joined it to the carbon. So let me highlight all of these. And now it's the iodide ion. Okay, so we're going to assess the frontier orbitals in this reaction. So the very first thing, now let's go up to the top. The very first thing, first idea, is that you're only going to look at the reactants and the curved arrows associated with them. Most chemicals have both a HOMO and a LUMO, but in any given reaction, they're not using both of them. They'll either use the HOMO or the LUMO. So we need to figure out who's using which, and then what is the exact nature of the orbital? What's the exact label of the orbital? Okay, so let's go back down to the example, and what we can see is the following. The first arrow that we drew originated at that lone pair. That suggests, along with the fact that it's pointing to the methyl iodide, that suggests that it's the hydroxide ion that's supplying the electrons to the methyl iodide. That means that the hydroxide ion is acting as a nucleophile, and as such, it will be using its HOMO. The methyl iodide is the recipient of those electrons. Therefore, it's the electrophile, which means that it must be using its LUMO. It has to have an empty orbital to accept the electrons. So going back up to the top, the HOMO is what the nucleophile or base uses. Now, typically, this is going to be one of two things. In this example, it's a lone pair. So the lone pair on the hydroxide that I highlighted initially, those are the electrons that are being used. But what kind of orbital are those in? Well, there's two labels you could put on this. So first of all, they're not involved in a bond. Those are non-bonding electrons. So they're going to occupy a non-bonding molecular orbital. So you could say NMO. That would be the specific label for the HOMO in this case. It's a non-bonding molecular orbital, just like we saw in the MO diagram for ammonia. However, you could also just take a shortcut to this. Now, the MO in HOMO or LUMO stands for molecular orbital. But remember that the way that we got that non-bonding orbital was to just relabel an sp3 orbital. The hybridization of the oxygen in the hydroxide ion, let me draw this a little bit differently so we can see this more clearly. That oxygen has 4 areas of electron density around it, so it's sp3 hybridized, which means that each of those lone pairs is contained in an sp3 orbital. So you could also call this an sp3 orbital. So if it's a lone pair, back up to the top, if it's a lone pair, then the label you would use would either be to say that it's a non-bonding molecular orbital, or you could use the hybrid orbital label. So use the hybrid orbital label by checking the hybridization of the atom with the lone pair. LP for lone pair. Okay. Now, the other case, which you'll see from time to time, more often than not, you'll see it being a lone pair, but the HOMO could also be a pi bond. So a nucleophile could be something like an alkene that uses its pi electrons to attack something else. So it could be a CC pi. Okay, we'll see examples of that as we go forward, but for now this is pretty good. Okay, so now let's think about the LUMO. The question you have to ask about the LUMO is the following. First of all, you recognize that it's the electrophile, or the acid, that would be using its LUMO in any chemical reaction. So the question you're going to ask is this one. Is a bond breaking in the electrophile? So is a bond breaking in the electrophile, or if it's an acid, the acid? So to find that out, you go back to the mechanism. And what you see is the following. In this mechanism, in the electrophile, so now you just want to look at the structure of the electrophile itself, there may or may not be a bond breaking in the nucleophile. From time to time that happens. But if there is, we don't care. All we care about is what's happening in the electrophile at this point. And so what we see is this arrow right here that I've just highlighted, and what that's telling us is that the carbon-iodine bond is breaking. If that bond is breaking, then what we need to do is think back to what we saw in the very first segment on molecular orbitals, where I told you that if we populate an antibonding orbital, the consequence of that is to break the corresponding bond. So we're going to back into the identity of the LUMO. What we notice is that the Ci sigma bond broke. That means that it was the Ci sigma star orbital that was involved. So the LUMO is the Ci sigma star. Now notice that you can't just say sigma star. You have to say Ci. You have to identify and specify the atoms involved in the bond. Okay, so up above here, when we ask the question, is a bond breaking in the electrophile? If the answer is yes, the LUMO is the antibonding orbital of the breaking bond. Okay, let's do another example, and then we'll be able to fill in a little more information. So this example is going to involve a carbocation. I'm going to redraw. I just don't like that carbocation for some reason. Let's make it a little bit larger. So a carbocation, which to remind you is a structure that has a carbon that has a positive formal charge, and that's going to react with water. So when those two get together, the mechanism looks like this. The water molecule attacks, we would say. It attacks the carbocation, and it does so by using one of the lone pairs on the oxygen. That lone pair is used to form a bond between the oxygen and the carbon. So tracking those electrons through the mechanism. Okay, so what are the frontier orbitals? Well, remember, first off, we only look at the reactants and the curved arrows that are there. We don't care about the HOMO and the LUMO in any of the products because those aren't reacting. So we only look at the reactants. We notice in this case that an arrow originates at water, at a lone pair on the water molecule, and points to the carbocation. That tells us that the water is acting as a nucleophile, and because it is, it's using its HOMO, and the carbocation, which is accepting that electron density, is acting as the electrophile, and as such, it's using its LUMO. Okay, so now let's identify specifically what is the HOMO. Well, it's a lone pair of electrons, so those are non-bonding electrons, and they will be held in a non-bonding molecular orbital. So we could use that label. Or we could use the hybridization label. So the hybridization of the oxygen in water is sp3, which means that those lone pairs are contained in sp3 orbitals. So you could also use that label as well. Okay, for the electrophile, let's go back up to the top. Remember that the question we have to ask is a bond breaking in the electrophile? Well, when we look at the electrophile, there are no curved arrows showing any bonds breaking there. So the answer to that is no. Okay, so now let's think about what that orbital could be. So the hybridization of the carbon with the positive charge is sp2. So it's sp2, and that means the following, that its valence orbitals are what? What are the valence orbitals present on an sp2 hybridized carbon? Take a minute and think about that. Pause the video. Okay, now that you're back, having thought about that, hopefully what you came up with is that the set of orbitals is sp2, 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 and p, like we talked about previously. The three sp2 orbitals are being used to make the bonds between the carbon that has the plus and the other three carbons. That leaves the p orbital. The p orbital has nothing in it. It's empty. So in this case, the LUMO is an empty p orbital. And so we can fill that detail in up above, that if there is no bond breaking in the electrophile or the acid, what that's telling us is that the LUMO is an empty p orbital. Okay, so now we have our guidelines. We can use these guidelines and assess pretty much any reaction mechanism, even if it's a reaction we haven't seen, we'll be able to identify frontier orbitals. So let's look at one more example, and that's going to be acetone and the methoxide ion. So this is an example of a reaction you won't see this semester. The first two you will. This one you'll see next semester if you go on in OChem, which I feel certain that you will. Even if that was not your initial plan, it's very addictive, as you're probably finding. Okay, so the thing on the left we've seen a few times. That's acetone. The thing on the right is something we haven't seen yet, but we're going to see a lot of, and a lot of things that look like this, and this is called a methoxide ion. So in this reaction, this is what happens. Okay, so the methoxide ion uses the pair of electrons that I just highlighted to form a bond to the carbonyl carbon in acetone, which causes the pi bond between the carbon and the oxygen in acetone to break toward the oxygen. So now the carbonyl oxygen, or what was the carbonyl oxygen, has three lone pairs, so it accrues a negative charge, and we have a new bond between oxygen and carbon. Okay, so how do we assess the frontier orbitals in this situation? Okay, so which one of these is supplying the electrons? Is it the acetone or the methoxide ion? If you said it was the methoxide ion, that would be correct. So the methoxide ion is the nucleophile. As such, it's using its HOMO. This is a non-bonding pair of electrons, and so we can specify that the HOMO is a non-bonding molecular orbital. Or, just like we did for the previous two examples, we can use the hybrid orbital label for what that lone pair is contained in, and that would be an sp3 orbital. That makes the acetone the electrophile. The arrow is pointing toward it, so it's accepting the electrons. Since it's accepting electrons, it must be using its LUMO. So remember, the question for the LUMO, to identify the LUMO, you would ask, is a bond breaking in the electrophile? The answer to that, in this case, is yes. And that relates to this arrow right here that I've just highlighted. If you compare the original structure to the product, what you see is that we lost the pi bond between carbon and oxygen. So that bond broke, so it's the anti-bonding orbital, which is the carbon-oxygen pi star, that would be involved here. We're going to get more practice assessing frontier orbitals and identifying frontier orbitals in our next notes packet. But for now, let's wrap this up with a sort of a general observation. And that observation is the following, that the interaction or mixing of a filled orbital and an empty orbital is stabilizing. What that means is that it brings down the energy of a pair of electrons So it brings down the energy of electrons, and thus it brings down the energy of the structure they're in. So when we stabilize electrons, we're stabilizing the structure, because it's only electrons that can move around like this to different energy levels. When we think about the nuclei themselves, the protons, those have fixed energies. They don't have a ladder of energies the way that the orbitals show us the electrons do. Let's use as our example for this the one that we looked at previously. So A as a nucleophile interacting with B as an electrophile to form an AB bond. So A is the nucleophile, and so it's using its HOMO, which is going to be an occupied orbital. B, on the other hand, is the electrophile, so it will be using its LUMO to participate in this reaction, which is an unoccupied orbital. So let's think about a picture as follows. Let's imagine the instant at which A and B get together and that bond forms. And let's draw a picture of what's happening. So let's say that this over here is the HOMO of A. And then over here on this side, this is the LUMO of B. The HOMO of A has a pair of electrons in it, and the LUMO of B, of course, is empty. When those two get together, they're going to mix the way we've seen orbitals mix in the past. They're going to mix in phase and out of phase. The in-phase combination is a bonding result. So we might call that the AB sigma orbital. And the out-of-phase combination, as you know, is the anti-bonding result. So we'll call that AB sigma star. Now remember, when something like this happens, when we bring together orbitals and mix them in and out of phase, the electrons that came in with those orbitals end up in our new orbitals. So the two electrons that came in with A are going to end up down here. So what's happened? Well, if we think about this difference in energy, so this delta E right here, ooh, that color is not showing up very well. Let's do this differently. Better. Okay, so this delta E. What's happened is that we have stabilized this pair of electrons by that amount of energy. And we did so through the interaction of a filled orbital and an empty one. So the interaction, once again, let's write this out so we remember this, the interaction of a filled orbital and an empty orbital stabilizes a pair of electrons. We'll just say stabilizes electrons. Thus stabilizing the structure they're in. Now, in reality, people don't draw molecular orbital diagrams like this for reactions. This is a molecular orbital diagram that doesn't really exist because in the instant that those two chemicals come together, a new chemical is formed. And so you really don't have a discrete HOMO of A and LUMO of B anymore. However, this would be a successful reaction because what you're doing is lowering the energy of a pair of electrons. So that would be a successful bond-forming expedition, if you will. Now, this idea of mixing a filled orbital and an empty orbital and stabilizing a pair of electrons also shows up in a different context that we'll see later on in the course. But it's a general idea that we can find application in a variety of contexts. So that concludes this set of notes, and so we will move on to set 3.